seem like a race.
All right, so workshop number 5, give mechanisms and products. So you have an alkyne, HBr, one equivalent, polar protic solvent. Pi bond reacts, we break the HBr bond. Carbocation on the more substituted carbon, right? This was a terminal alkyne. So one carbon was more substituted. Plus charge can be here or here, doesn't really matter. Polar protic solvent, we know that we have a polar protic solvent. It's going to be involved in the mechanism. Lone pair reacts there, adds in. We have an enol, and if we have an enol, we of course know we do a tautomerization. So we do the tautomerization, the pi bond takes the H. The 2 electrons in this OH bond now form a new pi bond. Br minus comes in, takes that H, and we end up with a ketone. So this is one of the ways to make a ketone. H plus in water with an alkyne makes a ketone. All right, next one, halogenation Cl2. Notice one equivalent, right? Be careful with the equivalences. Cl2, we all should know, recognize halogenation, no carbocations, 3-membered ring, SN2-like stuff. So 3 arrows, pi bond reacts, breaks the chlorine-chlorine bond. Lone pair from the front chlorine goes there. Doesn't matter which carbon here because they're both equally substituted. All right, here we go again. I'm back here. SN2-like, it doesn't matter which carbon we go for because they're equally substituted. Notice the trans addition, which is classic for the halogenations we've seen before. Again, only one equivalent. All right, same deal, Cl2, one equivalent, polar protic solvent. Notice also we have a terminal alkyne. All right, it's a little different, same 3 arrows, 3-membered ring. Notice the bond angles, careful with our bond angles, bond angles, bond angles, bond angles. SN2-like, again, now these 2 carbons are different. This one's more substituted. So do that SN2-like. We still have a plus charge on this oxygen, right? Polar protic solvent. Anytime you use those polar protic solvents, you should probably remember you probably need to do a deprotonation. All right, Cl minus comes, deprotonates, and we can't do a tautomerization because, right, we need another H here. There's not another H, so we can't do a tautomerization again. All right, similar to above, HBr, but now in excess, terminal alkyne. Again, plus charge on the more substituted carbon. Get the bromine there, keeps reacting, pi bond reacts, plus charge on the more substituted carbon. Notice this carbon, this can also do resonance. Remember we talked about that resonance structure. Adds in. Do we make any asymmetric centers? sp3 hybridized with 4 different things? Nope, 2 bromines, the same. So no, we don't need to worry about enantiomers there. All right. How about Br2 in excess? So halogenation twice. So we're going to add 4 bromines. The classic 3 arrows, 3-membered ring. Bromine needs to go to the more substituted carbon. Make sure we're balancing our charges. Right? When we make these 3-membered rings, there should be a plus charge whenever we added. The Br there. Trans addition, of course. Make sure you see that trans addition. Again, Br2, 3 arrows. Adds into the more substituted carbon. More substituted carbon, SN2-like. You can see the 2 bromines here are trans, wedged, hatched. These 2 bromines are trans as well. All right, mercury. Terminal alkyne with mercury. What does mercury add? Mercury adds the solvent and an H. 2 arrows, makes a 3-membered ring. Water goes to the more substituted carbon, SN2-like. Again here, we do a tauta. This is the one that has a double tautomerization. Right? So the pi bond goes there. The OH electrons form a new pi bond. This is the one with mercury. Remember with mercury, this is a catalyst, and it's mercury plus 1 here. We need to get rid of the mercury. So the mercury is not going to take electrons, it's going to give up electrons. Mercury is going to give up electrons. So it gives up electrons, pi bond breaks, those electrons go to the oxygen, and we do one more tautomerization, and we've regenerated our mercury catalyst here. We end up with a ketone. Mercury with water and alkynes makes ketones. So we're going to get a similar product as mercury, but a different mechanism. So acid catalyzed hydration, right? H2SO4, which you should know how to draw out. Pi bond reacts, terminal alkyne. Flipped it around here. So the plus charge is on this carbon, right? The more substituted one. Water, polar protic solvent. Water reacts. Tautomerization. But now we're not worrying about mercury. So all we're going to need to do is regenerate our catalyst. Make sure until you've regenerated the catalyst, you're not done. Deprotonates there, and we get our ketone. All right? Remember, catalysts need to be regenerated. You're not done with the mechanism until you regenerated the catalyst. Hydroboration with an alkyne. Again, boron has that empty p orbital, has that syn addition. This is the only way you know how to make the anti-Markovnikov, right? Where one of the things you're adding is on the less substituted carbon. So in this case, the boron goes to the less substituted carbon here. In that syn addition, the H and the boron are adding in a syn fashion. 2 arrows. The second step, you don't need to know the mechanism for. All you do is replace the BH2 with an OH. Then you got to be careful here, though, because guess what you just made? An enol. And what do enols do? If you see an enol, memorize it. Very good. Pi bond takes the H. The OH electrons here forms that new pi bond. And now instead of making a ketone, what did you make? You made an aldehyde. This is the only way you know how to make aldehydes. Alkynes, hydroboration oxidation makes aldehydes. Terminal alkyne, NaNH2. You see the Na and the NH2 have looks like a regular bond, right? But is that a covalent bond? Absolutely not. That's an ionic bond, so you can redraw it as plus and minus. What's this really strong base going to do? It's going to deprotonate a terminal alkyne. It's going to make it a good nucleophile. Step 2, you're going to add in a good electrophile, and you're going to do an SN2. And this is the only way you know how to make carbon-carbon bonds. So make sure you know how to do that. Don't add or lose carbons. When you draw an alkyne, what do? You draw the alkyne first. Bond angles matter. Make sure you get the right bond angles. Don't add or lose carbons. We also talked about making alkynes. Right? Strong base again, NaNH2, recognizing its ionic bond, N minus, 2 equivalences. We're going to do 2 E2s. Every time you do an elimination, you make a pi bond. So this is E2. What do you remember about E2? E2, the H and the leaving group need to be anti-periplanar, 3 arrows. Notice how I went for the H, that's anti-periplanar to this bromine. 3 arrows, make a pi bond. This H needs to be anti-periplanar to this bromine to make that second one. 2, 3, alkyne. Good. You've seen this a couple ways. This is an acid catalyzed tautomerization. Right? So what happens here? The pi bond is the nucleophile. Right? It goes for that H. And at the same time, you can have this OH bond break, and those 2 electrons form a pi bond. Right there. I've starred this H. Right? That's where this starred H ends up at. Right? It's catalyst. So you know the reaction's not done until you've regenerated H+. So I did it all in one step. This H is this H that's regenerated as H+. Classic reductions, you know the 3 ways. H2 Lindlars, syn addition, but it goes from alkyne to alkene, SP to sp2. Syn addition. H2 gas and palladium on carbon, it keeps reducing, right? You know H2 is a gas, so there's excess of it, you don't need to say it. It takes an alkyne and makes an alkane. If you wanted to make the trans alkene from alkyne, you need to use lithium dot or sodium dot in that solvent, and that makes the trans alkene. Ozonolysis for alkynes. Terminal alkyne, remember it turns that terminal carbon into CO2, and then the other side it turns into a carboxylic acid. Notice how the carbons are numbered, don't lose any carbons, but the difference between a terminal alkyne versus an internal one. Terminal one, the outside carbon makes CO2, the internal one makes carboxylic acid.